Let's start with the most fundamental mechanisms in our acid derivatives chapter. So interconversion of things that already have a C double bond O group. Let's go ahead and do acids and esters. Remember that if you are in acid conditions, then you are not going to have any negative ions around. You're going to have more cations. Things are going to be protonated. So the very first thing that happens in acid is the protonation of this alcohol here. So now you have a very electron poor carbon that can get attacked by the lone pair on the alcohol coming in as a nucleophile. We have methanol as our nucleophile this time. When this oxygen comes in, these electrons go onto this oxygen, so our tetrahedral intermediate with the new carbon-oxygen bond now has no positive charge up here on this oxygen. The methanol that came in has a positive charge on that oxygen because that lone pair got used. This oxygen only has one lone pair left now. Now these are reversible. The lone pair can come back down from this oxygen and kick out the methanol, especially since this is positively charged. This is the best leaving group out of the three. So in order to get one of these OH groups to leave, what has to happen is a proton transfer. So this proton has to go onto this oxygen instead, relieving the positive charge on this oxygen down here. So now the proton has transferred to this oxygen over here, making that the better leaving group. So then when these electrons go down, water can leave. So the thing that left is water. Now there's a positive charge on this oxygen over here, so a proton has to fall off to make that a regular looking ester here. So we now have the methyl ester instead of the carboxylic acid. If we have an ester instead of a carboxylic acid, we can have ethanol fall off instead of H2O falling off. It's a very similar mechanism. Again, we are an acid, so the first thing that happens is a protonation of this carbonyl oxygen here to make it more reactive. Again, we have our methanol coming in, and again we have that positive charge being relieved there. And now we have the tetrahedral intermediate. Whichever oxygen has the positive charge is the one that's more likely to leave. So if methanol can very easily leave, and you can get back the ethyl ester. If you have an excess of methanol, you're going to try to push the odds towards ethanol being the one that leaves, because if there's a lot of methanol around, methanol will just keep adding and keep adding and keep adding until it's more likely that ethanol is the one that leaves and ethanol will not find its way back to that molecule. So we need to have a proton transfer happen here to make the ethanol piece the better leaving group, so that when these electrons come down, the piece that leaves is ethanol. So ethanol has left over here. We have the methyl ester with a proton on the oxygen, so that proton has to leave, and that will give this ester over here without the proton. So again, this can keep going back and forth. Methanol can come in, ethanol can leave, ethanol can come back in, methanol can leave, methanol can come in back again, and then ethanol can leave. To get one ester over the other, you just want to have a lot more of the alcohol. So if you have a lot more methanol around, then when this ethanol falls off, the chances that it will find another ester and come back in are lower. It's much more likely that another methanol will come back in and that you'll still have the methyl ester at the end of it. You can also convert these in base conditions. So this time we're going to have more negatively charged intermediates in our mechanism. The only thing about the basic conditions, you just have to be careful that you don't have a lot of water around, because we'll see that if you have hydroxide, it's no longer in equilibrium. It goes to this side and you're stuck with the carboxylate. Carboxylates are not very reactive, so it's not going to react and go the other way. So if you want to convert one ester to another, just make sure there's no hydroxide around, otherwise you will get this product instead. The reaction mechanism itself is pretty similar. It's just that in base we do not have a lot of protons around, we do not have a lot of positive charges around. So our tetrahedral intermediate, instead of being positively charged, has a negative charge on this oxygen. And that oxygen has 3 lone pairs. I'm just going to draw one of these. This can come back in to reform the pi bond, and then it can kick out either one, the methanol or the ethanol. The key is that this is going back and forth, kicking out methanol, kicking out ethanol, and so in order to get one over the other, you have to treat it with an excess of one of the alcohols, and then that will push the products to the ester that you want to have. So if there's a lot of methoxide around, not a lot of ethoxide around, eventually we'll end up with the methyl ester, because there won't be a lot of ethanol around to find and reattack. The thing that's going to be attacking is methanol, because you have much more of that in your flask. So if you want that to happen, you do need to make sure there is much more methanol in your flask. And then you can drive it to being the methyl ester and not the ethyl ester. So if you do have water around, then the water will react with any methoxide or ethoxide that you have, and we'll have hydroxide as the attacking agent. Let's see what happens with that. Oh, I forgot my negative charge up here. I am sorry about that. Okay, so hydroxide definitely negatively charged. And then when it attacks here, it pushes the electrons up here, making the intermediate negatively charged as well. We have our tetrahedral intermediate with a negative charge on this oxygen. So this lone pair can come back and kick out the hydroxide. This step is reversible, so either one of these can happen. It can kick out the hydroxide, or it can kick out the ethoxide. So if it kicks out the hydroxide and goes back to this, then the hydroxide can come back in, so this can be in equilibrium. However, if it kicks out the ethoxide, you have these two products, and then what happens very quickly is an acid-base reaction, because ethoxide is much more basic than this carboxylate ion. So this acid-base reaction happens very quickly, because this carboxylic acid has a pKa of around 4 or 5, whereas the alcohol has a pKa of around 16. So this is much more basic. This is going to get a proton from this carboxylic acid, and the proton is not going to go back. And so instead of having an acid, we have a carboxylate ion, and this is not going to get attacked by ethanol. This is much less reactive than an ester. So we're going to drive all of this reaction to this end. This does not have a reversible arrow like the one above does. Let's take a look at some other acid derivatives, acid chlorides and anhydrides. Generally, these are done in neutral to basic conditions, because they would work in acid, but acid is not needed, and acid can cause side reactions. So for example, this acid chloride to ester releases HCl as a side product. So the H from the alcohol and the chlorine from the acid chloride are acidic. The chloride does not want to take up this proton, so the proton is hanging around, making acidic conditions, and so a lot of times a mild base like pyridine is present to soak up that proton to prevent it from doing side reactions that you don't want to happen. So let's go ahead and show that with that mild base around. First we'll have this oxygen come in and attack the electrophilic carbon. That gives an intermediate with a negative charge on this oxygen, a positive charge on this oxygen. Let's show a mild base taking this proton off of here. so that we don't have a positive charge on that oxygen anymore. That will make it less likely to be a leaving group. So we have protonated the base. This might be pyridine. We might have made a pyridinium ion. So we've gotten rid of that proton. That way when the lone pair comes back down off of the oxygen, this is no longer a very good leaving group, and so we know that chloride is going to leave instead. So we have our Cl minus. We have some sort of mild base that has grabbed our proton. So if we are using an amine instead of an alcohol, the amine can act as a base. It's just that we're going to need two equivalents of that. One is going to end up as the amide. The other one is going to soak up the protons. So if the amine is a fairly simple amine, fairly inexpensive, we can just go ahead and use two equivalents of that. So we'll go ahead and show this amine attacking, creating that tetrahedral intermediate again. This particular example has a primary amine attacking. You can attack with a secondary amine as well. So if one of these H's were another R group, that would also work. You can't have all three of these be R groups. So if you have a tertiary amine, something with 3 R groups and no protons, then this next step that I'm going to show can't happen, and this reaction won't really work. So what we have is a base. I'm going to draw just another equivalent of the amine. Show what happens with that. So we're going to go ahead and remove this proton so that this nitrogen is a much worse leaving group. We don't want the nitrogen to leave. We want that to stay on there. So now this amine down here, this amine has gone to be the protonated amine. This is no longer able to do any attacking, so that's why this is, you need to have two equivalents, because we can't have this amine forming amide now. It's kind of done. It's NH3R positive. There's no lone pair on that nitrogen that can do the attack that was shown on this first step. Okay, so then we have this lone pair coming in and the chloride getting kicked out. So here we have the chloride getting kicked out. We have one amine on here. The other amine has soaked up the proton, as we mentioned earlier. So we have a protonated amine. So here we have one amine here, the other amine here. So we need two equivalents, unless we have some different base to soak up the proton. Okay, so here, instead of HCl coming off, we have some sort of carboxylic acid coming off. I just drew acetic anhydride, so acetic acid would be the one that comes off. Generally, when you use acid anhydrides, they're fairly simple pieces. All right, so let's go ahead and show our alcohol, or this could also be water if the R group is another H instead of a methyl or ethyl piece. So we'll show this attacking, and we'll show the pi bond breaking to form our tetrahedral intermediate. And then we'll show just a base coming in to soak up this proton, just to make this more likely to stay. So this will not be eliminated here. Okay, so we've shown our base soaking up that proton. Maybe it's pyridine, maybe we have some pyridinium over here. So now we have a choice, instead of between an acetate and an alcohol leaving, we have an acetate or an alkoxide leaving. So this is definitely going to favor the acetate leaving. Remember, the better leaving group is the weaker base. Acetate is a weaker base than alkoxide because acetic acid is a stronger acid than alcohol. So we have this coming down to reform the pi bond, and this leaving, giving us our ester and our acetate. And then we also have some sort of mild base that has soaked up our proton. Those are the three things that we have. So similar to how the chloride went, when you have an amine, you will be using either an extra equivalent of the amine to soak up the proton, or some other sort of base to soak up the proton. Because if you only had one equivalent of the amine, some of the amine would not be able to react in your reaction to form amide. Some of the amine would be used to soak up the proton, to be used as a base. So if you want to make sure that all of your anhydride reacts, you need to have at least two equivalents of your amine around. So this amine, again, I've shown as a primary amine. You could use ammonia in this reaction if you want. You could use a secondary amine in this reaction. You could not use a tertiary amine because you need to have at least one proton attached to the nitrogen. You'll see that in just a moment we need to take one proton off of here. And so if the nitrogen starts without any protons on it, we are not going to be able to get this reaction to work. So here we have the nitrogen adding in, and this nitrogen is positively charged. So if all of these were R groups and couldn't be removed, then when this negative came back down, it would have to kick off the nitrogen. But since we do have at least one hydrogen on here, I'm going to show another equivalent of the amine pulling off that hydrogen. All right, so now this amine over here has just gone to the ammonium ion. There's no lone pair on there anymore, so this is just going to stay like that. It's not going to form an amide. Now that we have the nitrogen being neutral, it is definitely way more likely that the acetate will fall off instead, because nitrogen leaving as a negative nitrogen is very difficult to do. So now the lone pair comes down, reforms that pi bond. It's going to kick out the acetate because it's not going to kick out a negatively charged nitrogen. And this has a proton on it and it has an R group on it. Okay, and then we also have the ammonium, or some other base could be around to soak up a proton. We need something to soak up the proton there. So let's look at some reactions that are a little bit more difficult. These are less reactive starting materials. This amide is not as reactive, but if you heat it, let's put a little heat on here, you can get hydrolysis to happen in acid, or if you heat it even more strongly, you can get it to happen in base. So let's see what's going on over here. Again, with acid conditions, we need to have some protons playing a role. So the first thing that happens is the protonation of this oxygen here, so that when the nucleophile comes in, we have a neutral tetrahedral intermediate rather than one that is negatively charged. Okay, so what is coming in here is water. We don't have hydroxide, we are in acid, we are not in base. So we have water coming in here. So these R groups that are on the nitrogen can be R, they could be alkyl groups, they can be protons, so this can be a primary amide, secondary, tertiary amide, whatever you have there. Okay, and then we are going to go ahead and show the amine taking the proton here, because we want to make it a much better leaving group. A negatively charged nitrogen is not going to be a very good leaving group. So now we have that coming back down and reforming the pi bond. And then the other thing that we have here is the amine that has gotten kicked out. And since we have the amine around, we could go ahead and use this amine to take this proton off, and that will give us the products shown. So if you're in acidic conditions, you are not going to have just a neutral amine. Remember that this amine, this only exists at pH greater than 9, and if you're in acidic conditions, you're going to have the conjugate acid of the amine instead. In contrast, if you are in basic conditions, then you are going to have the amine, a pH higher than 9, let's say, or 9 or higher. We have the amine, but you are not going to have a carboxylic acid, because any pH greater than about 5, you will have the carboxylate instead of the carboxylic acid. So these are the products that you get in base, whereas these are the products that you get in acid. In acid, you get the conjugate acid forms. In base, you get the conjugate base forms of your products. The amide itself is neither an acid nor a base, so it looks like this in most pHs, or in all the pHs it looks like this. We did protonate it when we were in acidic conditions to make this temporary protonated intermediate to be able to do the reaction, but in general we have an amide being neither an acid nor a base. All right, so in basic conditions we're going to have hydroxide attack instead of water. If we have hydroxide around, that is a better nucleophile than water molecule, so we're going to use that one. And we are going to have to kick out this nitrogen, even though we said nitrogen is not a very good leaving group, especially it would leave as a negatively charged nitrogen. Your textbook shows it leaving as a negatively charged nitrogen and then grabbing the proton in the next step. I think that next step happens so quickly that we could show the nitrogen grabbing the proton on the way out, because I don't think that a negatively charged nitrogen would exist for very long. So I'm going to go ahead and show this as one step. So we have that pi bond reforming. This oxygen is missing its proton because the nitrogen grabbed it as it was leaving. So we have our products, the conjugate base form of an amine, the conjugate base form of a carboxylic acid. The acid or base hydrolysis of a nitrile goes through the hydrolysis of an amide. So we'll go ahead and take it up to the part where we have the amide, and then you can copy what we have for the amide up above. So in acid, we have a protonation happening of the lone pair on the nitrogen of the nitrile. So that makes this carbon even more electrophilic, even more electron poor, susceptible to attack. And this is hydrolysis. We're in water. And that forms a bond between the oxygen and the carbon. The oxygen now has a positive charge, and the nitrogen does not. It has a lone pair. Now we need to have a proton fall off of the oxygen to give it back a neutral charge. We also need to have the lone pair on the nitrogen get a proton from somewhere. So if I had drawn the lone pair closer, you could show the lone pair getting this hydrogen if you want to, but this can just fall off to solvent while this is getting taken off of the solvent. So now we have the oxygen with a neutral charge and the nitrogen with a positive charge. One of the lone pairs on oxygen can then get pushed in to form a double bond to carbon, making the bond to nitrogen a single bond. And this is now pretty much the amide, except that it has a proton on it. So if we have the proton fall off, and then maybe rotate this around so that it looks more normal, we can continue as we had above the acid hydrolysis of an amide, keep adding proton and then water and hydrolyze the amide like we showed up above. The base hydrolysis would be somewhat similar. It's just that we would not have protonated intermediates here. We're going to have negatively charged intermediates, hydroxide, instead of acid proton source. So that would give this negatively charged intermediate instead of the positively charged intermediate from over here. I'll go ahead and draw this proton out so that I can show the lone pair on nitrogen grabbing that proton, giving oxygen the negative charge instead. So now we have oxygen with the negative charge. We need to move that negative charge onto the nitrogen and then also relieve that negative charge, letting nitrogen take a proton from water. Okay, so I'm trying to show this lone pair going into bond to this carbon so that we have a double bond to oxygen, making it an amide. Instead of putting the negative charge on nitrogen, I went ahead and just grabbed a proton with that, and then these electrons that used to be between the hydrogen and the oxygen need to go onto the oxygen. So that leaves a hydroxide ion that is created when nitrogen grabs a proton from water, and now we have this amide. It's just turned it's just twisted in a different direction. We're used to seeing the oxygen maybe pointing up. And then we would continue as above with the base hydrolysis of the amide to get all the way to the carboxylate ion. So these next few reactions I think look a little bit less familiar. The other ones were starting to form kind of a pattern. So for a lithium aluminum hydride, we will go ahead and show the lone pair attacking that carbon and pushing one of the pi bonds up to nitrogen. So now we have this imine anion. An imine is something with a carbon double bonded to a nitrogen. They're generally pretty reactive. The thing that looks strange to me about this mechanism is that we need to have a second equivalent of negatively charged hydride ion add in here and kind of give the nitrogen -2 charge. We can't add a proton to this nitrogen like we were doing in the hydrolysis because we're not in water. Lithium aluminum hydride is not compatible with water, and having protons around would just degrade the lithium aluminum hydride, so we wouldn't be able to react it again. So your textbook draws this nitrogen as being sort of complexed to aluminum. So I'll show you that in just a moment. That has to try to help stabilize this negative charge because we need to have another negative charge here. So we get this very strange intermediate with effectively 2 negative charges on the nitrogen. So that's really crazy looking. Let's see your textbook how they show it. So in 20.7 in the textbook, they have a similar type of thing where it's complex to aluminum, and it doesn't look that pretty, but we know that lithium aluminum hydride can reduce nitriles, and this, and we know that there's no protons around before the second step in the quench, so that is the best explanation there. So we need to have these lone pairs go and grab some protons so that only one lone pair is left on the nitrogen. So that would give us a regular amine. And then if we were in pretty low pH, this could even have a third proton and be the ammonium ion. I went ahead and just drew the amine looking more normally down here below instead of with all these H's on carbons showing. All right, let's try a lithium aluminum hydride reduction on this amide. So we have a hydride adding in for that. So that puts a negative charge on the oxygen. The thing is that the oxygen now has to leave the molecule, so we have to have a negatively charged oxygen leave as O2 minus, which is kind of strange. So we have it complex to aluminum that is supposed to be helping out with this unusual mechanism step. Let's find that in your textbook as well. So here it shows the, even though the oxygen, I guess the negative charge on the oxygen isn't showing because it's complex to the aluminum, and so the electrons do leave with that oxygen. So we'll go ahead and show that in our mechanism as well. So we're going to go ahead and show these electrons on nitrogen adding in to the carbon and the bond to oxygen leaving with the oxygen, effectively a complex -2 oxygen ion leaving the molecule. So that does not seem like a very good leaving group, but once it does leave, then we obviously have a very electron poor species here for a second hydride to come in and attack. So since lithium aluminum hydride again is so reactive, we can't have these proton transfers in our mechanism like we would normally like to see, because we can't have any water or any proton donors, hydrogen bonding molecules around when we have the lithium aluminum hydride. It's too reactive. So the aluminum itself has to be complexing to these electronegative elements and stabilizing those what seems like excessive negative charges on them. So that second hydride coming in relieves the positive charge on that nitrogen, on the imine over here. So I've drawn this particular amine as a tertiary amide going to a tertiary amine with 2 R groups on the nitrogen. These could have been 1 H and 1 R. You could have had a secondary amide going to a secondary amine, or NH2 could work as well, and then you would have the primary amine like you do up above. So you could have any kind of amine coming from any kind of amide. Overall, if you're not doing the mechanism, if you're just doing the product, it just looks like you erased that double bond to oxygen, and now it's just missing, is what the product looks like. So any kind of amide can give any kind of amine. As opposed to up above, since you're starting with a nitrile, the nitrogen does not have any R groups on it. There's no methyl or ethyl on there, and so this is only going to give a primary amine as the possible product. Whereas with the amide, it's all 3 types of amines are possible because you're effectively just removing that oxygen. All right, so let's go ahead and do this reaction on a nitrile to give a ketone. I did not specify what Grignard you're using, so this could be a methyl, ethyl, benzene ring, whatever you have here. That carbon that is the last carbon on the chain that's connected to the magnesium effectively has that bond, those electrons, and so you have a negatively charged carbon of some sort. I'll just go ahead and draw that adding into the carbon. So this gives our amine with a negative charge on the nitrogen. So while the reaction is still going on, that could just be hanging out next to the positively charged magnesium. Then as you quench the reaction with some sort of aqueous workup, there's going to be a proton source around, so then that can just get the proton. So this one is just an imine rather than an imine ion. We've been working with some imines already. Something with a carbon double bonded to nitrogen. Normally the nitrogen without a charge would have that double bond to carbon and plus a bond to something else, either a hydrogen or some kind of alkyl group. So your textbook, as it shows this, it doesn't really show the imine formation because in water, imines tend to be easily hydrolyzed to give ketones. And so it refers you to figure 19.7, so the formation of imine, which we hadn't talked about yet. That's in the chapter on ketones because imines are similar to ketones. They're that same oxidation state, so they're more closely connected to ketones. So let's go ahead and continue that and actually show that mechanism, though. They just say that it's the reverse of that figure 19-7. Let's see, get that over here. So we'll go ahead and we'll show the reverse of that. Let's work through that. So at this step, we are done with the Grignard, and so we do have protons around. This is an aqueous workup here. So the first thing we need to do is make this a little bit acidic. So now that we have a positive charge on the nitrogen, we can have a lone pair from oxygen, a water molecule come in and attack the carbon and relieve that positive charge. So that gives us this intermediate. The positive charge is now on oxygen, not on nitrogen anymore. Nitrogen has its lone pair back. What we need to do is transfer this proton from the oxygen to the nitrogen. So you could either show the lone pair grabbing this proton, or you could show this proton falling off and another proton coming on, whichever you'd like to do. I'll go ahead and show this lone pair. I think I can get it all the way down to this hydrogen here. So now the positive charge has transferred from the oxygen to the nitrogen because the proton has moved from oxygen to nitrogen. So now that the nitrogen is positively charged, it's a decent leaving group. We can have this lone pair come into the carbon and the nitrogen leave. So we have ammonia there. And we have a ketone, except that it is positively charged, so we can just go ahead and let the proton fall off of there. And I'm also going to draw the ketone kind of pointing up. That's how we're used to seeing it. So here is our ketone product, similar to what was drawn over here in the original reaction. So here we have, again, the removal of an oxygen atom. and 2 hydrogens. So instead of just the lithium aluminum hydride reduction where we took the amide to the amine, we are removing the hydrogens as well. So we're removing H2O, that's why it is a dehydration. We're removing water from this to give the nitrile. And this uses the thionyl chloride reagent here. All right, so we're going to show this amide attacking thionyl chloride. So the lone pair on nitrogen is going to go into this carbon, and then the electrons are going to come from oxygen to bond to the sulfur. And we'll go ahead and show this in 2 steps, first going up to the oxygen and then letting the chloride leave, because it's not really an SN2 reaction if you have pi bonds around. So now we've kind of made the sulfur sort of a tetrahedral intermediate. We're going to go ahead and reform that bond to oxygen and kick out a chloride. So there's our chloride kicked out, and the oxygen is now bonded to sulfur, making this a much better leaving group. So let's go ahead and show at least one of these hydrogens leaving to give a more neutral compound. And then this is a pretty good leaving group. We're going to go ahead and show this getting kicked off, and in the process we're going to go ahead and lose this other hydrogen as well. So we're going to form a triple bond from the nitrogen to the carbon. That's what we have in our product. These electrons go onto the sulfur. The chloride leaves. That's giving us our nitrile. We had a couple protons leaving. I'll just put proton over here. We have the thionyl chloride leaving as SO2. We have another chloride around. So this is our dehydration using thionyl chloride. This is pretty similar to what we see with thionyl chloride for the conversion to an acid chloride, and to what we saw in the alcohol chapter when thionyl chloride was able to make alcohol into a chloride. So let's do a similar thing again, where we have the lone pair on this oxygen attack the sulfur, which pushes electrons up to the oxygen. Instead of drawing this on a second step, we'll just go ahead and have a lone pair on oxygen go back down to the sulfur, reforming that pi bond and kicking out that chlorine. So this adds in, the negative charge temporarily goes on oxygen, then that reforms and it kicks out the chlorine. Up above we showed that in 2 separate steps, but I'm just taking a little bit of a shortcut here. I think this would actually look better if we showed this lone pair going in, so that we don't have to have a negatively charged, a positively charged oxygen with a double bond. I was just checking to see if this was happening in some sort of pyridine or base solution, if I should have had this deprotonated first, but your textbook just has it in a neutral solvent, and there's a lot of acid, carboxylic acid around, so I'll just leave it with a positive charge. But I will go ahead and relieve that positive charge. And then we have some chlorides around from the first step that we showed here. We do have some chlorine around, so we're going to go ahead and just replace this, which is now a good leaving group, with the chloride. So if we wanted to, we probably could have even left this proton on here and have this be a neutral instead of a positive. I think it's a little bit unclear in your textbook whether this is taking place in acid solution or in more of a neutral or pyridine type of solution. So let me just draw that other option here, because I think that that would also work. If we think this is happening in slightly more acidic things and we don't want this negative charge around, we could just leave that proton on there, not let it fall off, and then just have the chlorine come in like that. So the only difference here is whether or not we want to have this oxygen with a negative charge. Either way, we need to have a lone pair from the oxygen come in and kick out the SO 2Cl. These electrons go on to the sulfur. And the things that fall off are a molecule of SO2 and Cl minus chloride ion. We could show that same thing without the negative oxygen intermediate if we want to. We could just have this still protonated and then have these electrons come in and kick out the group, which would lead to those same products. I was checking to see if there were any base around in these conditions. It seems like you could just use the thionyl chloride in the solvent, which would be fairly acidic, so you could go through this lower route without having any negatively charged intermediates there, except for chloride, which chloride can exist in acid as well because it's a very, very weak base. It's not really a base at all. So let's go ahead and show the ability to form amides if you have this special DCC reagent. Normally, if you just have the acid and the amine together, the only thing that's going to happen is a proton transfer from the acid to the amine, which is a base. All right, so let's go ahead and show this nitrogen, instead of the amine nitrogen grabbing the proton from the carboxylic acid. This is what DCC is. It's dicyclohexocarbyl diimide. So I'm going to draw each of these cyclohexane rings as just a CY to make this mechanism a little bit easier. So when you see CY, I'm just going to draw that instead of a cyclohexyl ring for the rest of the mechanism so that I can fit it in this space. So now we're going to go ahead and show this attacking the carbon of the diimide and relieving that positive charge. Okay, so we no longer have a negatively charged oxygen here. We have an oxygen that is attached to something that's activating it to be a leaving group now. Now we can have this amine come in and attack the carbonyl to try to start forming that amide. So we'll have this be our tetrahedral intermediate. All right, so now what has to happen here? We need to have this proton fall off so that we have a regular amine. Okay, so now that we have a neutral nitrogen, this is a much better leaving group. We do have to have this other nitrogen grab a proton in the process. Let's get ready with that. So we will reform this pi bond, and now we'll keep the amide and we'll lose the other group here. So this other group will have a double bond between the oxygen and the carbon, and this other set of electrons, get that pointing to there, we'll grab this hydrogen instead. Okay, so we have formed our amide product, and then the leaving group that left is actually a symmetrical urea over here. Each of these nitrogens now has a hydrogen attached to it, and they have those cyclohexane rings. I'll go ahead and draw them out. I think I can fit them one more time. So this is not the product that we care about, this urea over here. This came from DCC. What we are actually trying to form is this amide over here. But the DCC enabled that to happen because, as I mentioned before, without it, you just have an acid-base reaction and you get a carboxylate and an ammonium ion.